Yeah, it was good. So got a couple questions here. Just on focus on OChem. Not really worried about 102 right now because I got a midterm in like 2 weeks, and I'm also currently behind in that class, so I'll have to be catching up on that. Just mainly been focused on 261. I got a midterm on Tuesday. Also got a psych midterm coming up, and I also got another econ midterm this week as well. So yeah, not super fun, but guess we just continue on with life. So first thing here we have is we got a question just asking us to draw the most stable conformation of the molecule, show molecules shown below. So currently we have them in this kind of structure, but we want to get them into chair conformation. So yeah, I guess we'll just get started with the chair conformation. So first thing here is just to draw a chair conformation. I'm not really good at drawing these. These are low-key annoying to draw. But here we have the chair conformation. Now, in order for something to be the most stable, we want it to be on the we want the largest group to be on the equatorial position, not the axial position. Quick explanation. Actually, wait, no, first, what is equatorial, what is axial? So say we have this plane here. Just imagine looking at the ring from the side, and say this is like the plane of like the rings. You know, all of the rings are alternating in between this kind of equatorial plane, and yeah, like this, just the plane, right? So now an axial plane is what is perpendicular. So if it's like going up like this, that would be axial. If it's going down like this, that would be axial because that is perpendicular to this plane. You have a 90-degree angle right here, so that's axial. Now equatorial, bro, I didn't want to delete that. Now equatorial would be like along that line, that axis of that axis of the center. It would be like going like this, or it would be going like this. You know, that would be equatorial rather than axial. So in order for the most stable conformation to be drawn, we need to make sure the largest group or the largest attachment is on the equatorial plane. So yeah, I guess we'll just get started with it. So the first step is to find out what is actually the largest group. What is the largest group, you may ask? Largest group is this one right here. This is going to be the largest group. So here we got carbon 1, 2, 3, and 4. So carbon 1 is going to be this OH group. We'll just put down the equatorial. So equatorial up, this will be OH. Wait, Loki, this is too close to it. So we'll put this on equatorial up. So I'm not really sure like if it matters which way it goes, up or down, but I think it's supposed to go up because if we look at this from a bird's eye view, we can see that this is on the cone, right? Like the triangle, and that means it's going like out of the page. So if we look at it from the view that we're drawing this chair conformation in, this would be going up. So that's why I'm drawing it as equatorial up. Am I sure that this is right? No, I'm not really sure. So don't maybe take it for granted, but that's just how I see it, and it kind of makes sense to me. So here you have carbon 1, 2, 3, and 4. So carbon 1, carbon 2, carbon 3, and carbon 4. So this one here is cone, this is going up. So this one needs to be going down into the page. So that means these just have to be opposite. So this is equatorial up, this is equatorial down, this is going to be equatorial up, this is going to be equatorial down. But we need it to be down, so this will be equatorial down. So you might be asking, how did I count that? If this is equatorial up, this has to be equatorial down. You know, you can't have them like, you can't have this as equatorial up. You know, you can't have two equatorials up beside each other. It has to be equatorial down. So if you need an up conformation, then you have to do an axial up rather than equatorial up. That's just something to note. So yeah, so because this is up, this needs to be down. That's basically our drawing. Oh, I forgot to write the AOH here and then two groups here. So yeah, that is our final answer. That's the most stable conformation. Well, it should be, at least, if I'm not tweaking. I don't have the answer key with me right now, but I'm assuming that this is right. Hopefully it is right. And we'll just move on to the next question, which is this one. This is why we have two examples, because if I get the first one wrong, hopefully the second one will make more sense. So here we'll just draw another chair conformation. I low-key cooked on that drawing there, the first one. It low-key looks done nice. It's probably one of my best ones I've ever drawn. This one don't look that good. Okay, here, so we have to draw the most stable conformation, and in this case, all three of these attachments are methyl groups, so it doesn't really matter which one is on the equatorial and which one's on the axial, but we'll just start on the equatorial, carbon 1, we'll start this one right here. So this is coming out of the page, so we'll put this as up. I'm not sure that's right, not really, but that's just what's been working for me, and when I do these questions with that kind of methodology, I'm getting the question right, so I'm just assuming that that is right. So here we got carbon 1, carbon 2, carbon 3 is the next one, and we need this to be going down or into the page. So this is equatorial up, this is equatorial down, this is equatorial up, and this is the third carbon, but this needs to be going down, and we can't have equatorial down here because that's not how it works. It's going to be going axial down, so that's why we have a straight line going down. Yeah, that's why it's down. And now next we have equatorial down here, and here we have a down on carbon 4, like this going into the page, or this is just the opposite of what this first carbon was. So if this was up, then this will be down, and this is able to be equatorial down. So that is our final answer. That's our final confirmation, and that is the right answer because I have the answer key with me on this one. So yeah, those two questions pretty quick, pretty straightforward, yeah, we'll move on to the next one. So here we got a radical substitution reaction here. So got a couple questions here to answer just based off of the reaction. So the first step is to, what are the two major products of this? What is A and what is B? So in this substitution reaction, what will happen is that, so actually wait, like the two major products, maybe like I should start with what are the two propagation steps, but in this substitution reaction, the Br2 will split into two bromine radicals, and those bromine radicals will attach or hit it from the back. Like, bro, wait, pause. Wait, it'll hit a tertiary carbon from the back and bump off a hydrogen so that it takes its place. That's basically what's going on. So if you quickly imagine, it'll make more sense once I get into the propagation steps, but if you quickly imagine Br2 splitting into two, we got two bromine radicals, and then they're going to want to take off the carbon of a tertiary carbon. They're going to want to take off the hydrogen of a tertiary carbon. So the tertiary carbon is this one right here. It is attached to 3 carbons. This is a fourth degree carbon or a quaternary carbon. I really don't know how to say that, but yeah, so we're mainly just focused on this one right here. So the two major products will just be HBr, because we're knocking off a carbon from this structure, and then we're also getting this entire structure just with a bromine instead of a hydrogen there. So I guess I'll just draw that real quick. Boom. That is basically the answer for this one. Yeah, that's it. Yeah. So now the two propagation steps, this is where it'll kind of make more sense as to what's going on. So first, a Br radical will be by itself. After the initiation step is just when the Br2 splits into two bromine radicals, but we're not talking about the initiation steps. Maybe I should mention there's 3 main steps. There's 1, 2, 3. We got initiation, propagation. There's usually 2 steps for this one, and then termination, which has multiple different potential steps, usually 3. So we're just going to be focused on the propagation and the termination step, because the initiation step is literally just Br going Br1 and Br another one. So that's basically all initiation is, not really that complicated. And then termination is basically the complete opposite of that. So yeah, we'll just get started with the propagation step. A way to recognize if it's a propagation step is if we have a radical on both sides of the equation. So if we have a radical here, another radical there. That's how you know it's propagation. And yeah, I learned that from the organic chem tutor. Shout out organic chem tutor, bro. I really don't know how he does this, bro. But anyways, we have Br radical, and then we have this entire structure right here. So we got 1, 2, And we got a cyclohexane. Bro, I actually hate drawing these. This is so ugly. So we have this structure just brought down right here. So what will happen? Well, we have a hydrogen here, like I mentioned, and this bromine radical will come around and attack it. That was the wrong arrow. It should be a single because only one electron is moving down. And what we'll be left with is HBr because bromine and hydrogen are combining, and then we'll be left with that cyclohexane just without the bromine group, the hydrogen. So it'll just be this with a methyl group and a radical because missing that hydrogen. The hydrogen took the electron with it and it formed HBr, and it left one single electron because a single bond is made out of 2 electrons, stuff like that. So that's our first one. The second one here will just be this radical, this radical here. It'll just be finding another bromine radical and combining it together, and it'll leave another bromine radical. So I'm not sure if you're able to notice, but here we have one radical on this side and one radical on this side. That's how you know it's a propagation step, and that's how you know you did it correctly. So yeah, we got this now here. And now this will come into a 2 bromine, and this one will want to come into this place, and it'll split these 2 bromines so that one bromine will join into the radical here, and the bromine will just have another radical by itself. So just to save time, it is going to look exactly like this. The bromine will connect to that, and then we'll have a plus bromine radical because this one went over here and this one went over here. So yeah, that is the 2 propagation steps. Hopefully that made sense. And again, if you want to make sure we have one radical on this side and another radical on this side, and that's how you know that's a propagation step. So yeah, that is propagation steps. Now, one termination step. Termination step is just the opposite of initiation step. It's just 2 radicals combining into each other. So I'll just give you different potentials for the termination step so it kind of makes sense. So the first, most simple one that probably makes the most sense is just 2 Br radicals combining with each other. And that's one termination step. I feel like, I don't know, I read something like one of these is the least likely, but I'm not completely sure which one is which. But yeah, another termination step is just a Br radical combining with a cyclohexane radical thing that we have there. So I'll just quickly draw it out. Bro, this is so ugly. Plus a bromine radical. And we'll just be left with this exact same thing, pretty similar to the propagation step, except we're not going to have a Br radical at the end. Another potential propagation step is just these 2 radicals combining with each other, these 2 cyclohexane radicals. Cyclohexane is not the full name, but that's just what I'm just calling that for short. So we'll have this one here, and that will combine with another one of those, and we'll just be left with those 2 combined. But I feel like this one is highly unlikely, and it doesn't even mention this in the answer key, so it might not be true, but that's just something to think about. So yeah, that's pretty much it for this one. Pretty quick. Low-key running behind on time. Bro, I forgot that the time change was last night, bro, so low-key messed me up a bit, so because I lost an hour. But yeah, I'll see you tomorrow. Goodbye.